This video will be our first lesson in our module on graphs, and it will be a general introduction to graphs. We'll have lots of new terminology and some definitions, and we'll see several different types of graphs. So in this section, we'll introduce directed graphs as a way to visualize relations on a set. So a relation is a subset of the Cartesian product. So for example, I have the set here A equal to 0, 1, 2, and 3. And then the relation is going to be the set little r, lowercase r, equal to the set of ordered pairs 0, 0, 0, 3, 1, 2, 2, 1, 3, 2, and 2, 0. So this set R is a subset of the Cartesian product of A with itself. So we know that the Cartesian product of A with itself is a collection of ordered pairs where the first element comes from A and the second element also comes from A. And so R is just some subset of that Cartesian product. In representing this relation as a graph, elements of A are called the vertices of the graph. So you can see the elements of A, 0, 1, 2, and 3, are here in this graph below, figure 1.1. You have 1, 2, 3, and 0 in the little pink circles. Typically, the vertices of a graph, which are the elements of the set A, will be represented by labeled points or small circles, as we have here. We'll connect vertex A to vertex B with an arrow called an edge, going from vertex A to vertex B, if and only if A relates B. So you see it says A lowercase rb. Because our relation is called lowercase r, we write it this way, and we mean that A relates B. And what does it mean that A relates B? It means that A comma B belongs to the relation R. So this type of graph of a relation is called a directed graph or digraph. And it's directed because the edges have arrows indicating that the edge is initiating at one vertex and terminating at another vertex. So each edge has a direction, so this is a directed graph. So if we go back and look at our set R, we have the ordered pair. Let's say we have 2, 0, for example. 2, 0 is an ordered pair in our relation, and 2, 0 in this graph shows up as the edge initiating at 2 and terminating at 0. So that's the ordered pair 2, 0 shows up here in our graph. And the ordered pair 0, 3 shows up here in our graph. It's the edge initiating at 0 and terminating at 3. When we have an ordered pair like 0, 0, that's going to be this loop at 0. So 0 is related to itself by this loop. So if we go through the edges in the graph, we'll see that for each ordered pair we have exactly one edge, like we have an edge initiating at 1 and terminating at 2, and an edge initiating at 2 and terminating at 1. So those are the ordered pairs 1, 2, and 2, 1, respectively. Now I want to point out that the actual location of the vertices in a digraph is immaterial. So the location that we choose will be called an embedding of the graph, but there may be more than one way to embed the graph. The main idea is just to place the vertices in such a way that the graph is easy to read. So we might initially sketch a graph and find out that it's a little bit difficult to read and we want to move things around. As long as we preserve the direction of the edges and the number of edges and their locations, then we can redraw another draft of the graph. So there are many different ways to represent the same relation as a directed graph. And for example, you'll see figure 1.2 on your screen is actually the same graph as figure 1.1 above. It contains the same information. So you can see that we have the self loop from 0 to itself here, just like we had in the first graph. We have an edge from 0 to 3, just like we had in the first graph. We have an edge from 1 to 2 and an edge from 2 to 1. We also have the edge from 2 to 0 and the edge from 3 to 2. So all of the same edges as in the previous graph, but we've just moved the vertices around to make it look a little bit neater. This is perfectly legal, and this is the exact same graph. Just a little bit of terminology here. We are going to be most commonly referring to the vertex of the graph, but a vertex of a graph is also called a node, a point, or a junction. You might run into this other terminology. And we're also going to mostly stick with the term edge, but an edge of a graph can also be referred to as an arc, a line, or a branch. So you may run into this other terminology elsewhere. So we shouldn't be concerned if two graphs of the same relation look different, as long as the connections between the vertices are the same. So let's look at another directed graph. Consider the relation S, whose graph is as pictured in figure 1.4. What information does the picture give us? Well, first of all, right away, we can tell that the set A, on which we formed the relation S, consists of 1, 2, and 3, because these are 1, 2, and 3. It was a little blurry, so I just filled them in, but this is vertex 1, vertex 2, and vertex 3. So the set A should be 1, 2, 3. And we can also tell exactly which ordered pairs are in the relation just by reading the edges from the graph. So because we see that there's an edge initiating at 2 and terminating at 1, we know that 2, 1 must be in our relation. And because there's an edge initiating at 3 and terminating at 1, we know that 3, 1 must be in our relation, and so on. We know that 3, 3 must be in our relation because we have the self loop at the vertex 3. And exactly the ordered pairs that they've written here, we can see each one is present in the figure. So here's another example of a directed graph. In this example, we're giving a visualization of the relation of the set inclusion, the ordering of the subsets of a two-element set. So we begin with the two-element set capital B equal to 1, 2. And we want to take A to be the power set of B. So our vertices are going to be the subsets of B, as you can see we have here. There are 4 subsets of B. They are the empty set, singleton 1, singleton 2, and the set B itself. So these are the 4 vertices of the graph. And if a set is a subset of another set, then we'll have a directed edge initiating at the first set and terminating at the set that it's included in. So we can see from the graph that the empty set, well, that of course is a subset of every set, so it will have an edge initiating at the empty set, terminating at singleton 2, initiating at the empty set, terminating at the set B, initiating at the empty set, and terminating at the set singleton 1. So those are these edges here, 1, 2, and 3. And the empty set is also a subset of itself, so it has a loop here, initiating at itself and terminating at itself. Now each of the subsets is a subset of itself. Singleton 2 is a subset of singleton 2, singleton 1 is a subset of singleton 1, and B is a subset of B. So there are actually loops at all of these vertices. And then we have singleton 1 is a subset of B, singleton 2 is a subset of B. So this graph gives us a visualization of the relation of the set inclusion. Okay, another definition will be that of a simple directed graph. A simple directed graph consists of a non-empty set of vertices. We're often going to denote a set of vertices by capital V. and a set of edges, which we'll often denote by capital E, that is a subset of the set B cross B. So all of the graphs, all of the examples we've seen so far are simple directed graphs. Some terminology and comments here. Each edge is an ordered pair of elements from the vertex set. The first entry, you might have heard me using this word, is the initial vertex of the edge. So the edge starts at the first entry of the ordered pair. And the second entry is the terminal vertex. So the edge ends at the second entry in the ordered pair, and hence the arrow points at that vertex. So here's an example, another example of a simple directed graph. So we're going to call the set of vertices V and the set of edges E. So just from looking at the graph, this is S, A, and B. So just from looking at the graph right away, we can tell that V should be the set S, A, B. And then we can also find the edge set just by reading the graph. We have an edge initiating at S and terminating at B, so we have S, B. Initiating at S and terminating at A, so we have S, A. Initiating at A and terminating at B, so we have A, B. We also have an edge initiating at B and terminating at A, so we have B, A. And we have a loop from B to itself, so we have B, B. Now you might notice that in this picture, each edge is labeled either 0 or 1. And we're going to come back to this example and we'll explain why they're labeled 0 or 1 later. But there are often reasons for labeling simple graphs or more complicated graphs as well. Some labels will make the graph easier to discuss, or others may have some other significance. In certain cases, it might be necessary to have more than one edge between two vertices. So that brings us to the definition of a multigraph. A multigraph will be a set of vertices, capital V, with a set of edges that can contain more than one edge between the vertices. So one note here is that if we identify a graph as being a multigraph, it doesn't necessarily mean that there will be more than two edges between some vertices. It just means that it's allowed to have more edges. And so they note here that it's similar to the idea of a square being a particular type of rectangle. All squares are rectangles, but not all rectangles are squares. We have the same thing with multigraphs. A common occurrence of a multigraph might be a road map. The cities and towns on the map could be thought of as the vertices, while the roads would be thought of as the edges. We know that it's not uncommon to have more than one road connecting two cities. So in order to give clear directions, we name the roads or number the roads so that we can direct someone how to travel from one city to another. So we're going to use the same method to describe the edges of a multigraph. Here's an example of a multigraph, as in figure 1.13. And you can see that if I just said the edge connecting 1 to 2, or initiating at 1 and terminating at 2, it wouldn't be clear which edge I'm talking about. Just like if I said take the road from city 1 to city 2, you might not know which road I was talking about. So we'd give the edges names in this case. So this is E1, little e1, this is E2, E3, E4, E5, and so on. So in giving these edges names and then using the names, we no longer have any ambiguity about which edge we're talking about. Whereas if we just gave the initial vertex and the terminal vertex, it wouldn't be clear. There are also cases where the order of the vertices is not significant. So it's not significant which is the initial and which is the terminal. And we'll use a different model for this situation, which is called an undirected graph. An undirected graph will consist of a set V, called a vertex set, and a set E. But now the edge set E is no longer sets of ordered pairs, it's just going to be sets of 2-element subsets of V. Then the 2-element sets are just visualized as lines connecting the vertices, and we no longer have the arrows. So here's an example in figure 1.16a. Here's an example of an undirected graph. So you can see I have vertices A, B, C, D, and E, and they're connected by edges, but it's not clearly indicated that any vertex is an initial or a terminal vertex of an edge. The edges are just there, so they don't have a direction. This is called an undirected graph. So an undirected graph like this might be a good model for a network of computers. If we labeled the computers A, B, C, D, and E, the way we would interpret this graph is that anywhere you see an edge is a direct line of two-way communication between two computers. So A has direct communication with D and B, and it's direct two-way communication so the computers can talk to each other. So this type of relation is what is called a symmetric relation. A relation is symmetric if we always have the property that if X can communicate with Y, then Y can communicate with X. So if the two-way communication is always there, we would call this relation symmetric. Now, we could use directed edges here, but it would simply clutter the graph. Since every connection is a two-way connection, we can just simplify things by drawing it this way. So in terms of the vertices, the graph above, which is also pictured here, is A, B, C, D, and E. That's the vertex set. And then the edge set, instead of ordered pairs, we just have these 2-element subsets. So we have A, comma B, because A has a direct two-way connection with B, and A, comma D, because A has a direct two-way connection with D, and so on. We could also have included B, comma A, for example, but we know that B, comma A is equal to A, comma B. So the order doesn't matter in a set like this. So when we have an undirected graph, we just use subsets instead of ordered pairs. There are several other situations where this graph could serve as a model. One of them would be, again, to think of a road map and interpret the vertices as cities and the edges as roads. Another abstraction might be that this is the floor plan of a house. So vertex A is your front door, and all of the other vertices represent rooms, and then there's a connection between the rooms if there's a door. So A would be like the outside of the house, and if there's a door to a given room, then it's connected by an edge. And probably you could come up with many other interpretations for such a graph, or many other situations where such a graph would fit. An undirected graph is called complete if every pair of distinct vertices is connected to one another. So if the graph has n vertices and every pair of distinct vertices is connected, we'll call that graph complete. And such a graph is generally denoted by using capital K sub n, where n is the number of vertices. So the capital K doesn't change, the little n will change. Here's an example of a labeled graph. A common example of a labeled graph is a flowchart. And as you can see in this flowchart, we require labels for most of the vertices and edges. So this particular flowchart illustrates the problem-solving process. At the start of the process, we're at the vertex labeled start, here on the top left. And at the end, if we're lucky enough to have solved the problem, we'll be at the vertex labeled end. The sequence of vertices that we pass through as we move from start to end will be called a path. The start vertex is called the initial vertex of the path. The end vertex is called the final or terminal vertex of the path. Suppose that the problem is solved after 2 attempts. Then the path that is taken will be start RAQLAQ end. So we'll go up and see what we mean by that. So we said the problem was taking 2 attempts to solve. So we're at start, and then we move to R. Then from R, we move to A. So we receive the problem, then we attempt a solution. Then we ask ourselves, is the problem solved? That's Q. And the answer is no, we didn't solve the problem the first time. So we'll learn from our mistakes. That's L. Attempt a solution, A. Then we go back up this edge to Q. Is the problem solved? And now we say yes, we solved the problem on the second attempt. So we go to end. So we wanted to describe this path in terms of the vertices that we visited. It's start, R, A, Q, L, A, Q, end. An alternate way to describe the path would be to list the edges that were used. So we could say we traveled down the edge 1, then 2, then 3, then the edge no, then the edge 4, then 3, and then yes. So we could also describe this path in terms of the labels for the edges. Then the description would be 1, 2, 3, no, 4, 3, yes. The second method of describing the path has the advantage of being applicable for multigraphs. Again, we already talked about how in a multigraph, just describing something in terms of the vertices is not clear enough. So instead, we would like to describe the path in terms of the actual labels for the edges. Figure 1.21 is an organizational graph that shows the leadership structure of a corporation. Such a leadership structure would often be represented visually in this way. The principle behind the structure is that everyone except the president has a single immediate supervisor, as we can see, and any action that anyone takes can reach the president only through a unique chain of command. This chain of command property is characteristic of a special type of graph called a tree. So this is just one example of a tree, and we'll see more examples of trees in the future. We note that the edges of the graph are not directed, but the relation between 2 connecting vertices is still clear. The top vertex is the supervisor of the lower vertex. So this has a top-down structure. So from the examples we've seen so far, we can see that although a graph can be defined as a collection of vertices and edges, an integral part of most graphs is going to be labeling the vertices and edges, and that will allow us to interpret the graph as a model for some specific situation. So we'll continue with a few more examples like this to illustrate this point. In the first example here, I'm going to return to the graph that we saw before with the edges having the numbers 0 and 1, and we said we'd come back and understand why they were labeled that way. So that graph looked like the one I'm drawing here now. It was a simple directed graph, and each of the edges was labeled with a 0 or a 1. So labeling the graph this way, we can use this graph to represent a set of strings of 0s and 1s, and in particular, a set of strings of 0s and 1s that have no consecutive 1s. So consider any path starting at the vertex S. If the label on each graph is considered to be the output of a printer, then the output will have no consecutive 1s. For example, they give the path SABBABBAB. If we followed this path, we would see from S to A is 1, from A to B is 0, from B to B is also 0, then from B to A is 1, from A to B is 0, looping back to B is 0, then again going back to A is 1, and looping back to B is 0. So the output of the path would result in 1, 0, 0, 1, 0, 0, 1, 0. Conversely, any string with no consecutive 1s could be determined by a path in the graph starting at S. Another type of graph that we'll see is what is called a tournament graph. In the picture below, we're supposing that four teams are competing in a round-robin sporting event. A round-robin sporting event is when each team plays each other team once, and each game is played until a winner is determined. So if the teams are called A, B, C, and D, and we label our vertices A, B, C, and D, then we can define the relation where two vertices are related. X is related with Y if X has beaten Y. So we need these directed edges. If we call this relation beta, then we would write X beta Y for X relates Y. And that would mean that X has beaten Y. So for example, one graph would look like this one here, and we could see from the graph that, well, it looks like A has beaten B because A is related to B. And it looks like A beat D, but then I can clearly see that D beat B, and so on. There are all of these relationships here, and we can read them in that way. There are many types of tournaments, and they could all be modeled by slightly different graphs. A tournament graph is a directed graph with the property that no edge connects a vertex to itself, because obviously a team cannot compete with itself. And between any two vertices, there's at most one edge. A complete or round-robin tournament graph, like the one above, is a tournament graph with the property that between any two distinct vertices, there is exactly one edge. A single elimination tournament graph is a tournament graph with the properties that one vertex has no edge terminating at it and at least one edge initiating from it, and that vertex will be the champion. Every other vertex is terminal vertex of exactly one edge, because it's single elimination. And there is a path from the champion vertex to every other vertex. So let's see an example of that. The Major League Baseball championship is decided with a single elimination tournament, where each game is actually a series of games. Until 1995, the two divisional champions in the American League, East and West, compete in a series of games. The loser is eliminated, and the winner competes against the winner of the National League Series, which is decided the same way. The tournament graph of the 1983 championship is below in figure 1.27. So this is a single elimination tournament. And we know that one team should be the champion. And from looking at this graph, the only vertex that has no edges terminating there is Baltimore. So we would conclude that Baltimore must be the champion. And clearly I can see that Baltimore beat the team from Chicago. Baltimore also beat the team from Philadelphia. And it doesn't look like Baltimore directly had to play Los Angeles, but Los Angeles was beaten by Philadelphia. So there is a path through Philadelphia from Baltimore to Los Angeles. So this meets the three conditions for being a single elimination tournament, because we have the vertex Baltimore has no edge terminating at it and at least one edge initiating from it. Each of the other vertex is the terminal vertex of exactly one edge, and there is a path from the champion, Baltimore, to each of the other vertices. So before we do some exercises in this section, we're just going to go through a bunch of vocabulary words here. You don't have to memorize them all at exactly this point, but these are the vocabulary words that are going to come up throughout this module on graphs, some of them. So we're introducing a bit of terminology here that you'll see again in the future. Now, of course, we've already seen the definition of a graph, a collection of vertices, some of which are connected by edges. More precisely, we can define a graph as a pair of sets, which are often denoted capital V and capital E, where V is a set of vertices and E is a set of two-element subsets of V, or ordered pairs. We will say that two vertices are adjacent if they are connected by an edge. two edges are adjacent if they share a vertex. So very soon we'll introduce what's called an adjacency matrix, and that will be a matrix that stores this data about which vertices are adjacent. A bipartite graph is a graph for which it is possible to divide the vertices into two disjoint sets such that there are no edges between any two vertices in the same set. We know already what a complete graph is, a complete in which every pair of vertices has an edge connecting them, or another way of saying that is every pair of vertices is adjacent. So therefore, a complete bipartite graph is a bipartite graph for which every vertex in the first set is adjacent to every vertex in the second set. A similar notion is the notion of connectedness. A graph is connected if there's a path from any vertex to any other vertex. Now we remember that a path doesn't mean a direct connection. We may have to travel through other vertices on our way, but if there is a path connecting any vertex to any other vertex, we call this graph connected. We're also going to learn in the future about graph coloring, and so that will introduce the definition of the chromatic number, which will be the minimum number of colors required in a proper vertex coloring of a graph. So we'll see that in the future. A cycle will be a path that starts and stops at the same vertex, but contains no other repeated vertices. The degree of a vertex is going to be the number of edges incident to a vertex, so the number of edges coming in and out. Down here, we're going to have a walk. A walk is a sequence of vertices such that the consecutive vertices in the sequence are adjacent in the graph. A walk in which no vertex is repeated is called simple. And that brings us to the definition of an Euler path. An Euler path is a walk which uses each edge exactly once. Or we could also have what's called an Euler circuit. An Euler path which starts and stops at the same vertex is called an Euler circuit. We already know that a multigraph is just like a graph, but can contain multiple edges between two vertices as well as single edge loops. A planar graph is often a very nice thing that we'll want to find. A planar graph is a graph which can be drawn in the plane without any edges crossing. A subgraph, well, that's very intuitive. We say that H is a subgraph of G if every vertex and edge of H is also a vertex or edge of G. And then we'll say that H is an induced subgraph of G if every vertex of H is a vertex of G and each pair of vertices in H are adjacent in H, if and only if they are adjacent in G. A tree is a connected graph with no cycles. A non-connected graph with no cycles is called a forest. And the vertices in a tree with degree 1 are called leaves. And vertex coloring will be an assignment of colors to each of the vertices of a graph. A vertex coloring is proper if adjacent vertices are always colored differently. Then just a little bit of notation here. We've already seen capital K sub n will denote a complete graph on n vertices. If we have a complete bipartite graph with sets of m and n vertices, then we'll denote that K sub m comma n. A cycle on n vertices will be C sub n, and a path on n vertices, P sub n. And here are some examples of what these could look like. The complete graph on 5 vertices should look roughly this way. The complete bipartite graph on 2 and 3 vertices would look like this. A cycle on 6 vertices like this, and a path on 5 vertices here on the right. So these are not the only way we could draw these. We know that with graphs, the placement of the vertices is not important, but this would be the most standard way for each of these examples. Now let's work through a couple exercises together. The first question is, what is the significance of the fact that there is a path connecting vertex B with every other vertex in figure 1.16a as it applies to various situations that it models? So I'm going to remind you that 1.16a was the graph we saw that we said could model a computer network or maybe a road map or maybe the floor plan of a house. So it looked roughly like this. This was an undirected graph, so we said anywhere that we had an edge, there was direct two-way connection between the vertices. So if this is a computer network, then the significance of the fact that there's a path connecting B to every other vertex would be that B can communicate directly with all of the other computers. Or similarly, if we said that this was modeling a map of roads, then we could say that the city B has direct roads connecting it to all the other cities. Or if we were thinking of this as the floor plan of a house, then we could say that B is a room that has doors to all the other rooms in the house. So some sort of central room. Okay, the next question. Draw a graph similar to figure 1.10 that represents the set of strings of zeros and ones containing no more than two consecutive ones. So figure 1.10 was a picture that we saw with the zeros and ones labeled on the graph. So perhaps we could start with vertex S for start, and then B and A as we had before. And I could label them 0 and 1. But I want to make sure that I have strings containing no more than two consecutive ones. So if I start with 1, then I can have one more 1 connecting A to B. But then my only choice must be 0. So then I should have 0 connecting me back to A. And at A, I could again have 0. And that should be a graph where any string that we could generate from this graph would have only no more than two consecutive ones, at most two consecutive ones. On the other hand, we could try to draw a directed graph that models the set of strings of zeros and ones where all of the ones must appear consecutively. So I would start kind of the same way. Maybe I have A down here and B here, and my first choice is either 0 or 1. Then I want all of the ones to appear consecutively. So if I haven't chosen a 1 yet, if I've gone down the path and chosen 0, then I can still choose either 0 or 1. But as soon as I choose 1, then my choice should be 1. Or I can go back to choosing 0, but once I go back to choosing 0, then all I have are zeros thereafter. So something like this. So this would be a graph that models the set of strings of zeros and ones where all of the ones have to appear consecutively. The next question is, in the NCAA Final Four basketball tournament, the East champion plays the West champion, and the champions from the Mid-East and the Midwest play. The winners of the two games play for the national championship. We're supposed to draw the 8 different single elimination tournament graphs that could occur. So we have the East, West, Mid-East, and Midwest teams. I'm going to draw them in. And we're told that first the East champion will play the West champion. So I'm just going to say maybe the East champion beats the West champion. And so I'm going to have my arrow pointing from East to West. And then I'm going to say maybe the Mid-East champion also beat the Midwest champion. So I have an arrow pointing from Mid-East to Midwest. So now the two teams that haven't been eliminated are East and Mid-East. These two teams are going to play, and one of them will beat the other. Let's say the East beats the Mid-East. So that's one potential single elimination tournament graph where the East is the champion and they've beaten the West and the Mid-East. We could also have East beating West and Mid-East beating Midwest, but then when Mid-East and East meet for the championship, maybe Mid-East wins. Then that would look like this, and Mid-East would then be the champion in this situation. Or I could have that East beats West, let's say that West beats East. West beats East. Mid-East is still beating Midwest. So now the two teams that are going to play for the championship would be West and Mid-East. And let's say Mid-East is the winner. Or we could have West beats East. And again, Mid-East has beaten Midwest. So the two teams that play for the championship will be West and Mid-East. But maybe now West is going to win. So the edge will initiate at West and terminate at Mid-East. Also, I could have East beats West, but Midwest beats Mid-East. So I have the arrow pointing at Mid-East. So now Midwest and East are going to face off for the championship. And let's say Midwest has won. So the arrow points at East. Or I could have East beats West, and Mid-East is beaten by Midwest. So again, I have Midwest and East meeting for the championship, but then maybe East wins. And what other situations could I have? I could have West beats East, and Midwest beats Mid-East. Then I have West and Midwest playing for the championship, and maybe West is the champion. Or I could have that West beats East, and Midwest beats Mid-East. And so West and Midwest play for the championship, but maybe Midwest is the champion. So now if I look around, I do have exactly 8 different tournament graphs and exactly 2 graphs for each champion, each possible champion. So these are all of the different ways that this single elimination tournament could be played. Then the last question here is, what is the maximum number of edges in a simple undirected graph with 8 vertices? So I'm going to draw in 8 vertices, and I'm just drawing them sort of at random. I think that looks like 8 vertices. A simple undirected graph means that each vertex could be connected to each other vertex with at most one edge. and I could just start sort of connecting them at random. So the question is, how many different ways could I draw such an edge like I've just drawn? I just chose two random vertices and I drew an edge. Well, the answer is as many ways as I can choose two vertices from 8. So 8 choose 2. If I choose two vertices from 8 and I connect them with an edge, however many different ways I can do that is the maximum number of edges in a simple undirected graph, because the word simple indicates that we'll just have one such edge between any two vertices. So 8 choose 2, we know that's 8 factorial over 8 minus 2 factorial times 2 factorial, which is 8 factorial over 6 factorial times 2 factorial. And I'll just work it out one time to remind us how the factorials are working. We'll have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 8 factorial on top. Then 6 times 5 times 4 times 3 times 2 times 1 from the 6 factorial. I also have 2 factorial, so I have 2 times 1. So then if I want to start canceling things from top and bottom, I can see that the 6 factorial will completely go away, and it's going to leave me with 8 times 7 over 2, which is 56 over 2, which is 28. So 28 is the maximum number of edges in a simple undirected graph with 8 vertices. So we'll conclude this video here. This will be our introduction to graphs, and we'll have more lessons in the next video.